What if I told you that our generation, and likely the next 10 generations, will never set foot on Pluto? This isn't science fiction pessimism. It's a stark reality, dictated by the unyielding laws of physics and the colossal scale of our solar system. We've sent probes, captured breathtaking images, but a human mission to the edge of our celestial neighborhood remains a distant dream. Today we're going to explore the monumental challenges that make a crewed mission to Pluto practically impossible, and what would happen if we dared to try. To understand the sheer scale of this journey, let's start with a simple comparison. A flight from New York to London takes about 7 hours. The Apollo astronauts took 3 days to reach the Moon. But Pluto, at its closest, Pluto is 4.28 billion kilometers from Earth. That's nearly 30 times the distance from the Earth to the Sun. At its farthest, it's a staggering 7.5 billion kilometers away. To get a human crew there, we need speed. Serious speed. Let's consider the fastest object ever launched by humanity, the New Horizons probe, which gave us our first close-up look at Pluto. It left Earth at over 58,000 kilometers per hour. Even at that incredible velocity, it took 9.5 years to reach its destination. A human mission would face an even longer journey. Why? Because a probe is light. A spaceship capable of supporting a human crew for years would be immensely heavier. It needs living quarters, life support systems, food, water, radiation shielding, and fuel for the return trip. All this mass requires exponentially more energy to accelerate. Using our current rocket technology, a mission to Pluto would be a one-way trip lasting over a decade. And that's just getting there. Imagine spending 10 years of your life confined to a small capsule, hurtling through the empty black void of space. The psychological toll alone would be immense. But the physical challenges are even more daunting. The first major hurdle is propulsion. Chemical rockets, the kind that got us to the Moon, are powerful but incredibly inefficient for long-duration travel. They burn through massive amounts of fuel in a short burst to achieve initial velocity. To carry enough chemical fuel for a round trip to Pluto, the spacecraft would need to be astronomically large, making it impossible to launch from Earth. We would need a revolutionary propulsion system, something like nuclear thermal or nuclear electric propulsion. These systems offer much higher efficiency, allowing for continuous thrust over long periods. A nuclear-powered ship could potentially cut the travel time in half, maybe down to 5 or 6 years each way. But even this shortcut presents a 12-year round trip, a timeline that pushes the limits of human endurance and hardware reliability. Next up is the brutal reality of space itself: radiation. Outside the protective bubble of Earth's magnetic field, space is flooded with cosmic rays and solar radiation. These high-energy particles can shred DNA, increase cancer risk, and damage the central nervous system. A decade-long exposure would be a death sentence without significant shielding. But shielding is heavy. Adding layers of lead or water to the spacecraft increases its mass, which brings us back to the propulsion problem. It's a vicious cycle. We need more speed to reduce travel time and radiation exposure, but the technology for that speed requires a heavier ship, which in turn is harder to accelerate. Then there's the simple but critical problem of life support. How do you pack enough food, water, and air for a mission that could last over a decade? Recycling systems would be essential, but even the most advanced systems on the International Space Station are not 100% efficient. They require maintenance and spare parts. Over 12 years, the probability of a critical system failure approaches certainty. Every component, from the air scrubbers to the water purifiers, would need to be flawlessly reliable for more than a decade. We simply haven't built anything that can guarantee that level of performance without a team of engineers on hand. And what about the human body? Extended time in zero gravity wreaks havoc on our physiology. Bones lose density, muscles atrophy, and our cardiovascular system weakens. Even with rigorous exercise regimes, astronauts on the ISS struggle to counteract these effects after just 6 months. A 12-year journey would cause irreversible damage. The astronauts might arrive at Pluto too weak to even perform their mission, let alone survive the long journey back home. But let's suspend disbelief for a moment. Imagine we've solved all these problems. We have a super-fast nuclear-powered ship, perfect radiation shielding, and flawless life support. Our crew of astronauts finally arrives at Pluto after a 5-year journey. What would they find? They would be entering a world of extreme cold and near total darkness. Pluto's surface temperature hovers around -230 degrees Celsius, cold enough to freeze nitrogen solid. The sun, from that distance, would appear as just a very bright star, providing little light and almost no warmth. The surface is a landscape of frozen nitrogen, methane, and carbon monoxide ices, with towering mountains of solid water ice. Landing on Pluto would be an engineering nightmare. We know very little about its surface composition and terrain in detail. Is the nitrogen ice firm enough to land on, or is it soft and slushy like a planetary snow cone? A lander would need to be designed to handle a complete unknown, with powerful heaters to prevent its systems from freezing instantly. Once on the surface, the astronauts would step out into a world under a dim, twilight sky. Their suits would need incredible insulation and a robust power source to protect them from the lethal cold. And what about the return journey? After completing their mission, they would have to launch off Pluto's surface, a feat that requires its own rocket system. They would then embark on another 5-year trip back to Earth, hoping that all their systems continue to function perfectly. By the time they returned, they would have been gone for over a decade, their bodies weakened and their minds forever changed by the profound isolation. This is the crucial point, the overwhelming reality check. A human mission to Pluto isn't just one single challenge. It's a cascade of interconnected, monumental problems. Advancements in propulsion, life support, and radiation shielding are all required simultaneously. A breakthrough in one area is useless without breakthroughs in all the others. The sheer complexity and cost put this endeavor firmly beyond our current technological horizon. We are talking about a project that would dwarf the Apollo program, requiring global cooperation and a budget that would make a moon mission look cheap. So, while our robotic emissaries will continue to explore the outer reaches of our solar system, sending back incredible data and images, the dream of a human footprint on Pluto's icy plains will likely remain just that, a dream. It serves as a powerful reminder of our limitations, but also as an inspiration. The challenges of reaching Pluto drive us to innovate, to push the boundaries of science and engineering. Maybe one day, centuries from now, our descendants will have the technology to make this journey. They will look back at our time and see us as the pioneers who took the very first steps. The universe is vast, and our journey through it has just begun. The impossibility of today is the challenge for tomorrow. Thank you for watching. If you were fascinated by this journey to the edge of what's possible, be sure to hit the like button and subscribe for more deep dives into science and space. And check out our other video on what it would take to build a base on Mars. See you next time.